Hi all, welcome to session 16. In this session I'm going to be looking at technical aspects of hang gliding, so principles of flight and a few things, design parameters of hang gliders to do with stability and so forth. So this is a little bit techy. You might need to take some notes as there's quite a bit of jargon, I'm afraid, involved in this session. Okay, so the prerequisites for gliding flight. Let's start right at the beginning. If you have a 25 kilo hang glider and a 25 kilo, I don't know, canoe, and you're on top of a cliff and you jump off, then the hang glider, assuming it's rigged, is going to give you a gliding flight and the canoe is not. So why? What is the fundamental difference? Well, the first thing we need for gliding flight is we need a reasonably large area. So obviously a rigged hang glider is 13, 14, maybe 15 square meters in area, and it will massively increase the coefficient of drag, so it will sink much more slowly. So that's the first step, and that's obviously the basis of an emergency parachute system. It's just a high coefficient of drag. But to glide, apart from area, an adequate area, we need a couple of other things as well. We're going to move forward through the air rather than go straight down, so we need some airspeed. We need to have forward speed. Airspeed is the speed of the air over the surface that is gliding from the front to the back. So that's definition. So we've got our airspeed and our area. The next thing we require is a suitable angle of attack. What's an angle of attack? Well, that is basically the angle at which the airflow meets that surface. So in the case of a hang glider, it's a wing. It's the relative airflow from the direction of travel over the top and bottom surfaces of the wing. So we need a suitable angle of attack. Those are the basic prerequisites that, that we need. But if you have a flat plate or something like that, then the air finds it very difficult to change direction suddenly. So rather than just a flat area, it is possible to have say a sheet of paper that will glide flat, but it's got a very thin margin of error. If it goes slightly too high, the wing will stall. It's slightly too, or tail slide or something like that, or drop nose down. So it's not very stable. And the reason for that is an air mass that has to change direction as it goes over the top of the lifting surface. And if it's a straight line, obviously it's an abrupt change of direction, which air doesn't like to do. But if you have a curved surface, it's much easier to kind of persuade it around the corner, a bit like a car going around a bend. Therefore, we really want a curved shape, and we prefer the aerofoil shape. So if we take a curve, even quite a subtle curve, like I've shown here, and you add your airspeed and your correct angle of attack, then you'll get a gliding surface. So I'm going to look here in a smoke tunnel. Here is, just to illustrate what I was talking about, this is a flat plate, and the green streamers are smoke, as you can see. The plate unfortunately is green as well, which doesn't help. You can see that as you increase the angle, it begins to stall, and the airflow over the top breaks away very quickly. So not very efficient for us in order to fly with. But if you use an aerofoil section like this in the same smoke tunnel, you can see we can actually alter the angle of attack significantly, and because it's kind of persuaded over that curved surface, the air adheres at quite a range of angles of attack, which gives us a range of air speeds at which we can glide. So the aerofoil is, as you know, is the favoured shape for a wing for flying. So there are different kinds of aerofoils, and slightly different shapes have slightly different properties. I won't go into it all now. It doesn't even need to be double surfaced. It can be a single surfaced aerofoil. As long as it's got that curve and it's got the right angle of attack, it will function. So the different shapes are used. Some are better at high speeds. Some have better glides. Some can fly more slowly or have a slower, slightly lower angle at which they stall, and so forth. So established that we've got an aerofoil, how does it actually help us? Why is that good? The reason really is that it generates some lift as it travels along, so it flies through the air. So how does it do that? Well, when an airfoil encounters an airflow at the right speed, the air is split into two streams. There's bits that goes underneath and the part that goes over the top, obviously. The part that goes over the top is accelerated slightly as it travels over the curve. If you look at this diagram, this is a venturi tube, which is basically a tube with a constriction. And you can see there, as you pass gas or any liquid through it, it will accelerate as it gets constricted. Same as pinching the end of a hose pipe. It'll actually accelerate the water flow through it. So we don't have a full venturi tube, but we do have a curved top surface. So the air as it hits is actually accelerated as it travels over that curve, as it's constricted, if you like. Not as much as a full tube, but sufficient to generate a loss of pressure. So what's that about? Well, when you have a venturi and you have an accelerated fluid or gas, the pressure drops, and that is Bernoulli's theorem. So as it goes over the top surface and it's accelerated, the pressure reduces, and therefore you get relatively lower pressure above the aerofoil and relatively higher pressure below the aerofoil, the bits at the positive angle of attack. And the difference between the two generates lift, simply because the high pressure wants to get to the low pressure, or the low pressure sucks the high pressure, doesn't matter how you work it out. Therefore, if you have all these elements in place, you will get gliding flight, because lift will be generated and get a much flatter and more efficient glide than if you just used a flat plate. So that's the basics of it. That's the venturi effect and Bernoulli's theorem, which explains about the lowering in pressure. Okay. In the actual fact, as mentioned earlier, we don't have a top surface. So the top surface, if you like, is the general atmospheric pressure. If a bit of air, block of air, if you like, if you want to visualize it like that, hits something and there's a curved aerofoil there, it actually gets slightly compressed as it goes over the top. Compression is the wrong word, constricted as it goes over the top, so that it actually accelerates. Okay. Right. Now we're going to look at the forces on an aerofoil. We've already mentioned that you need airflow, so the airflow has to be at the right angle, obviously in the right direction from the front to the back of the aerofoil. And we've already mentioned that we get lower pressure above a functioning aerofoil and higher pressure underneath. So it's all shown on this diagram here. A few other things are shown. Because of the difference between the high and the low pressure, we get a lifting force, and that operates forwards and upwards. In fact, it operates at 90 degrees to the direction of travel of the wing. There's another force on here, and that is drag, which is shown, and that's 180 degrees to the direction of travel. So it's always upwards and backwards. As mentioned in the glider, you're always flying forwards and downwards, so the drag is always immediately behind you where you've just come from. And then finally there's weight, which is the motive force, what pulls us along really, because we've got weight pulling us straight down towards the planet. I say straight down. In level flight, when you're flying with the wings level, it's straight down. If we're banked flight, it becomes slightly different. So those are the forces acting on an aerofoil. If you look on here, there's a dotted line on here as well, which is the sum of the drag and the lift combined, and we call that the resultant. So that's the resultant force that has any kind of upward force, and that is always diametrically opposite to the weight, which is in this case pulling straight down. So there's basically are the forces on an aerofoil, and to get all those balanced, you end up with a direction of travel, the glide path, as shown here, probably coming towards me on this diagram. Okay, so if you bear that little picture in mind, it'll help you visualize what's going on. The stall. Now, what I've described with the higher and lower pressure works if the angle of attack is within suitable range. But if you increase the angle of attack too much, on a hang glider, you do it by pushing out on the bar, right out, eventually the aerofoil will stall. A good way to visualize this is water. If you have a sort of curved rock, like a weir, for example, in a stream, the water will flow over it fairly smoothly. But if you keep making it steeper and steeper, eventually it will reach a point where the water cannot adhere. It can't change direction that quickly, and it'll start to break up and have a chaotic flow. And air is no different. If you increase the angle of attack far enough, the air hitting it will gradually no longer be able to make that change of direction, rather as we discussed earlier with the plate, and it will start to break up and you'll get a chaotic flow as shown on this diagram, and then you lose the pressure difference, you lose your lift. You might still have a little bit of drag, so it still drops you more slowly than the old canoe that we talked about to start with, but it is very inefficient. So that's the stall, and it occurs when the angle of attack is too high. A few other terms here that we need to get to grips with about how the hang glider moves. The first one is pitch. Pitch is a rotation about a lateral axis. So if you imagine a line going through you as the pilot, whether you're seated or prone, going across from tip to tip, pitch is that way. So it's nose up or down. That's the definition of it, a rotation through a lateral axis. The next one we've got here is roll. Roll is banking. So it's when one tip goes down and the other one goes up. So that's a rotation through a longitudinal axis fore and aft, and that's bank. And yaw, the third one, is through a vertical axis, so it's down through a king post if you've got a king post on your hang glider, so it's like that sort of twisting movement. So when you're turning or moving a hang glider, it's almost always a combination of all three of those. It rolls, banks over, starts to turn, twists like that, and the nose comes up or down as it goes, as it pitches. So it's a combination, and it's that pitch, roll, yaw coordination that allows us to fly a hang glider reasonably efficiently and effectively. So it's important to understand what those terms mean. Excuse me. Some more jargon, I'm afraid, here that we're getting to get into. Chord. Chord spelt with an H. The chord line, I think I've already mentioned, is a line drawn from the centre, the trailing edge, through to the centre of the leading edge. So the trailing edge is the back of the aerofoil, the sharp bit, and the leading edge is the blunt part at the front. So the chord line is drawn through those. So a little diagram there showing the chord line. And it also shows the next thing we want to talk about as well, which is the angle of attack. Mention the angle, that's what it is. Technically, the angle of attack is the relative angle between the airflow and the chord line of your aerofoil or of your wing. That's your AOA, angle of attack. Aspect ratio, another term you might come across. We've all heard of aspect ratio to do with TVs, for example, or perhaps some other things, and it's no different with a hang glider. It's basically an expression of the ratio between the chord, the average chord, or the mean chord, if you like, of the wing, so front to back, and the span of the wing. So a high aspect ratio is like something like an albatross, or in terms of a hang glider, we're talking about high performance hang glider, like an Atos or something like this, has a high aspect ratio. But a short, beginner's training glider, in terms of birds, again, a blackbird or something like that, has a short wingspan and therefore has a low aspect ratio. So the wider the aspect ratio is, the harder it is to control in a way. So it gives you better performance, and I'll talk about why in just a moment. And you get better glide performance. So this is why competition type gliders are all high aspect ratio gliders, but it reduces the stability. It becomes harder to make it stable, and also, in our case, crucially affects the handling. So because we're a weight shift, it's very difficult to have effective weight shift control on a high aspect ratio glider. There's all sorts of tricks to try and make that better. But that's what it is, aspect ratio. It's a measure of the shape. So it's low stability, high performance is the high aspect ratio, and higher stability and easy handling, but lower performance for a low aspect ratio glider. And then final thing I want to mention is the centre of pressure. If you're looking for one of these on your hang glider, you won't be able to find it because it doesn't exist. In actual fact, there are different amounts of lift being produced all over the lifting surface of the hang glider. But for the purposes of these diagrams, and so we can understand the forces, we talk about them all acting through this black dot you can see in the centre, which is the centre of pressure. That should be called the centre of pressure difference, really. So, it's a rotation around which everything else operates, with drag, direction of travel, the resultant, and your weight. So that's the centre of pressure. Okay, yet more techie stuff. Reflex. Reflex is actually a stability, a pitch stability mechanism. What it actually is that when you have an aerofoil, it generates lift, but if you lower the nose, it'll just keep going down. So we need some way of, we want a pitch stable aircraft. So if we go fast and then we let go, it'll actually slow down again. So it'll return to normal. So it's a kind of self-stabilizing system. And on a hang glider, we use a reflex. And reflex is basically a little kick up at the back part of the wing. A trailing edge is often held up by anti-luff lines, or out towards the tips you've got little rods or whatever that hold them up. And this reflex is that little upward kick. So when it goes down and the nose is dropping here in a steep dive, there's a bit of pressure on the back of the wing which helps to rotate the nose up again. Simple as that. There's various mechanisms for using it, but that's what reflex is. The next one that I want to talk about is dihedral. I'm still on pitch stability reflex. You can see here there's a picture, and you see because we've got a swept wing, we don't need a tailplane. On an aircraft with a sort of parallel wing, it would be unstable in pitch. But because we've got a swept wing, then the wingtips are behind us, and therefore they can be used as an up elevator to push it back up with the reflex built in there. And the mechanisms we do, I've mentioned, are the anti-luff lines and those rods out towards your tip to stop the sail from collapsing. Sometimes you get a very high aspect ratio glider, as already mentioned, and it doesn't have sufficient pitch stability. So classic example is the Atos rigid wing. As already mentioned, this is a very high performance glider. It's not got very much sweep on it, so for stability they put a tail on the higher performance versions. There are some rigid wings without tails, but the flatter, the faster, and the higher the aspect ratio becomes, the more you need something behind you to help you pitch out of a turn if you don't want to tumble. So a tail here, in the same way that a conventional aircraft or a sailplane has a tail. Okay, so dihedral. Dihedral, just a technical term, and it basically means that the wings are not generating lift entirely vertically because they're set at a slight angle. So the diagram says it better than I can in words. Basically, if the wing tips are slightly higher than the root, then the lifting reaction from each wing is operating slightly inwards. So when you start to roll, the first thing that happens is you get more lift on the lower wing, and it tries to go back again. It's stable. So a glider with a lot of dihedral, you turn it, let go, and it recovers to straight flight. The opposite of that is anhedral. Next picture. The anhedral here is when it goes the other way. So as you turn, a bit of resistance to your turn, they get you more lift on the upper wing. So once it starts turning, it goes really fast. And aircraft where you want a high degree of maneuverability, classic one is the Harrier jump jet, had very massive anhedral, and it was incredibly unstable. You move the stick, it would just roll over onto its back. So much so that it had to be controlled with computers because human beings couldn't hold it straight because it was unstable. But it made it nice and agile. Anyway, it's always good in a dogfight. However, that's what anhedral is. But the reality in a hang glider is we've got a mixture. What we actually have is this, and it varies from model to model and make to make, but essentially the frame is usually set to be slightly anhedral, but because the leading edges bend when they're under load, you get a little bit of dihedral, and also the sail billows up more towards the tips than it does towards the center. So you have parts of the wing that are effectively slightly anhedral and parts that are dihedral. And the purpose of all these design parameters, which are, I don't want to get into the design details of different hang gliders, but essentially they're made to try and give you coordinated handling, so that with the pitch coordination and with a balanced roll thing, that you can actually move a hang glider across fairly easily and it'll stay pretty well where you put it. If you have a 30-degree angle of bank, it should stay there with very little input. Sometimes it doesn't quite work, sometimes it goes a little bit steep and you have to high side it. Sometimes it'll keep trying to roll out and you have to keep nudging it in. But basically it's that balance so that you can steer it by weight shift. Almost every other aircraft, including paragliders, are controlled by aerodynamic control. So it's quite a black art flying a glider effectively by using weight shift alone. Okay, so that's anhedral, dihedral. A couple of the terms you'll hear mentioned are washout and billow. So washout. Washout actually refers to the fact that not all the wing is flying at the same angle of attack. Washout means that there is a lower angle of attack as you approach the tip of the wing. So the highest angle of attack is near the root, near the kegel if you like, and a lower angle of attack out near the tip. This is a very desirable thing in a hang glider. The reason why is that, as we've already mentioned, you stall at a certain angle of attack. Now pilots often talk about stall speed. And what they're referring to is the fact the stall occurs at pretty well the same airspeed all the time. And that's a very close correlation, so that's fine. However, it's not the actual reason. The reason that something stalls isn't the speed. The reason it stalls is because the angle of attack is too high, so the air can't adhere to the top surface. So if you have a wing with a lower angle of attack towards the tip, and you increase the angle of attack of the whole aircraft at the same time, obviously the bit that's going to stall first is the root, is round the centre. And that's exactly what happens on a hang glider. So a little diagram here. This is an airfoil in a smoke tunnel. That's another one I've superimposed on there, showing an airfoil at a slightly different angle of attack towards the tip. Okay, so what will happen is, as you increase the angle of attack, you can see the middle airfoil there starts to stall. the airflow breaks up, but the one at the tip, even though it's increased the angle of attack, hasn't got quite to the stall point. So the reality is you end up with no lift in the middle of the aircraft, but still have lift at the tips. And this has a number of effects. The first and most important is that the stall comes on quite gently. It's stalled a bit and gets a bit mushy before the whole thing goes, so it's much easier to cope with. The second thing is, because the tips are still supported while the centre, when you're coming into land, even if you're not absolutely perfectly straight or into wind or whatever, you'll still get a bit of lift on each tip, so it's quite stable when you push out and reach the stall point. So it resists spinning. If you had a completely flat wing, then when you slow down, if one tip went went a fraction of a second before the other one, the thing would spin. So it's a kind of anti-spin arrangement as well. But also in a hang glider, and this is quite subtle, because the wingtips are behind the centre of gravity of the pilot, what happens is, because the centre loses its lift, but there's still lift behind, is it tips the nose down. So when you fly up and you stall and you let go, what happens is the nose drops by itself because there's lift behind you, tips you down, re-establishes the airflow, the airfoil starts to work and it recovers. So it's a kind of auto stability mechanism. So that's why we have washout on a hang glider. Right, variable geometry. Doesn't usually affect you on training gliders, or probably the first glider you buy, but higher performance gliders, you'll see pilots have a string on their base bar which they can pull, and what it does is it operates a pulley system which pulls back the cross tubes, the floating cross tubes. And that has a number of effects, and it gets a bit complex now, but essentially as it pulls it back, it pushes out the leading edges, which flattens the sail, and it also makes the glider go slightly more anhedral because the wing wires are now going slightly further out position, of course, so it comes down a little bit. So you have different things happening. The major effect is it flattens the sail, certainly in the middle part, and therefore it makes it more efficient. A flat sail is less stable from a washout position, and it's harder to turn, so it's harder for you to move the sail when you move around, but it does give it a better glide and more speed. So the reason I have variable geometry is if someone is in a nice long glide between, say, one cloud and the next, they can yank on their VG, tighten up the glider and have a really flat glide to get the maximum performance. And then when they need a bit of handling, or they want it to be a bit more reactive for landing, they can slacken it off again, or for using a bumpy thermal, for example, where handling is more important. So that's what variable geometry is. Many pilots have them on high performance gliders. Some of them use them all the time, some don't use it all that much, but that's what it is. Okay, we're looking at drag now. There are two, I mentioned drag in the forces acting on the aerofoil, and there are two basic families of drag. You will hear terms like form drag and skin friction and interference drag and things, but as far as we're concerned, we're interested in the two main families, which is profile drag and induced drag. So profile drag is just the drag of anything being pushed through the air. It's the interference shoving the air out of the way. And you see from the diagram here, you can imagine it, stick your hand out the car window, it's what you can feel, and we can minimize that by streamlining. And this is why we have nice slippery pod harnesses, why we have aerofoil uprights and base bars, that kind of thing. Or in the case of higher performance gliders, why they remove the king post and all that altogether to minimize profile drag. So the more slippery the aircraft, as you can go back to the original forces, the better your lift drag ratio is going to be and the flatter your glide will become, so the better the performance. So that's profile drag. There's another kind of drag as well, which is induced drag, and this is slightly different. Induced drag is where the airflow going over the top of the aerofoil is travelling, as mentioned, a little bit faster, and it reaches the trailing edge before the air that goes underneath the aerofoil. So you get two molecules next to each other, one over the top goes faster and gets there more quickly. So there's this kind of interference where the airflow has to be re-established behind the trailing edge of the glider. And in actual fact, because we've got swept wings and all that, the actual airflow over the top and the airflow underneath are at slightly different directions as well. So there's a few things to sort out again when you get back to the trailing edge of the glider. And that produces a little bit of drag. So manufacturers try and make them as clean and sharp as possible and bury all the battens end to try and minimize that drag. But nevertheless, there'll always be induced drag along the trailing edge. But that's only a small part of it. The majority of induced drag is caused at the wingtips. The reason for this is that, as established earlier on, we have lower pressure above the top of the wing and higher pressure underneath. So going back to our water analogy, if you stick something in a stream and you have high water level, high water pressure on one side and lower on the other, it's immediately going to try and swirl round. If the thing's got an end, which we obviously have, we've got an infinite wing, so it'll swirl around, and that's exactly what happens. The low pressure underneath escapes round the wingtip over to the top, and as the aircraft is flying along, it leaves two vortices behind it. In fact, you fly behind another aircraft, be it a light aircraft or a hang glider or a paraglider, you'll feel that little bump as you go through their vortices. They leave these bumps behind, and that rotation, chaotic flow of the air, is quite a large contributor to the net drag of the aircraft. So that's induced drag. So why on earth are we bothered to separate up induced drag with profile drag? Drag is drag, right? Well, they've got one important property which they have different to each other, and looking at this graph shows you how. So ID is induced drag. So the faster you go, in fact the lower your angle of attack, so the more you pull in on a hang glider, the less the pressure difference and the less induced drag you get. In fact, very fast aircraft like fighter jets and everything have almost no induced drag because they're just flying at a very low angle of attack. Profile drag, however, is different. The faster you go, the more profile drag you get. In fact, if you double your airspeed, you'll quadruple the drag. And this is why a sports car and a van with the same side engine in, the sports car will always be faster because it's a smoother, slipperier shape. The van has a lot of frontal air and will generate a lot of profile drag. So, as you go faster, your profile drag gets greater, but your induced drag gets lower. So we plotted this here. You can see there profile drag and induced drag, and the top line, the U-shaped line there, is total drag. So if you add them both together, that's the drag profile of your aircraft. So you can see from that, fairly straightforward, the best area to have the minimum amount of drag for the lift that you're generating is at the bottom of the U. So we've got a bit of a sort of sweet spot there over a few miles an hour where it's quite efficient and has the minimum drag. So that's what we want to aim at, really. Okay, so that's drag, induced, profile and total. Just want to touch on soaring flight. Well, we're on principles. What is soaring flight? Well, we all want to soar, we want to stay up. But as we've already established, a hang glider works, a glider works because weight, dragging it down towards the planet, is what gives us our motive force. All that's happening is we're using the air with this clever thing called an aerofoil to vector that force sideways. And so we slide sideways, or glide if you prefer. So how can we stay up? Well, the answer is very simple. With a glider, unless you put an engine on it, all you can do is find air that is going up faster than you're sinking. So that's the key to soaring flight. Glider's always flying forwards, always flying downwards. So you find an air mass that is going up. So if you're sinking at 300 feet per minute, you've got to find air with a vertical component of 300 feet per minute plus in order for you to stay off the ground. Simple as that. In terms of miles an hour, if we're sinking at 1.2 meters per second, that's about 3 miles per hour. So we need 3 miles an hour, or 5 kilometers per hour if you prefer, a vertical component to the air to stay up. In actual fact, we need more than that because we add drag every time we turn. We're not very efficient. And also the air is never totally vertical. Even on a vertical cliff, there's still, the wind is moving along or it wouldn't work. So we have a horizontal component to the air. So you realistically need, 7 or 8 miles an hour of wind, probably even on a big steep cliff, to have enough vertical component to stay up. So that is soaring. It doesn't matter if it's ridge lift or a thermal or convergence or whatever it may be. There are various sources of lift, but that's what we need, a good vertical component. So that's soaring flight. Okay, next thing up is a little bit technical looking. This is a polar curve. A polar curve is just a map of the performance of your aircraft. So the axes here are speed, airspeed, this is horizontally, and vertical speed going up and down here. So we put in our thing and it looks like this is a curve. And that is actually a plot of the performance of your aircraft. So it shows the different sink rate at each different speed. So on this one, we look at the minimum sink rate, so that's right at the top of the curve. At the top of the curve, so we plot that in, that happens at 180 feet per minute. I think I've put in here is the minimum sink rate, and it occurs, we read it off, at about 24 miles per hour, something like that. No, sorry, 20 miles an hour. 20 miles an hour for your minimum sink rate. Okay, so that's worth knowing, which is basically, you know, fairly slow. However, we can get some other bits of information off this as well. We can work out where the stall is going to be. In fact, the curve stops before it reaches the axis, because once the glider's stalled, it just plummets downwards basically, so there's nowhere else for the curve to go. So we can plot the stall speed a little bit slower than the minimum sink, obviously. But notice the curve, so when you're flying out, you can be at minimum sink and then you fly a little bit slower and you reduce your performance before it fully stalls. And that's when just the root of the wing is starting to stall, but most of it's still lifting, sort of mushing flight, if you like. It becomes harder to control and it keeps trying to speed up. And if you slow down even more, the performance gets even worse. And eventually the nose drops and it loses all its lift. So that's the stall point. Okay. Another thing we can get off here, if we draw a line from the intersection of the axes here and a tangent with the curve, that will actually read off where our best lift drag ratio is, so the maximum glide. And on this one here, I've plotted it in to me, so it's at about 25 miles an hour, so a little bit faster. So worth knowing that your minimum sink is at sort of 20, 21, something like that, but your best glide is a little bit faster. And it's worth knowing that because a lot of pilots, when they're flying, especially in experience, will fly in lift and they'll fly around slowly at minimum sink, and then they'll hit a bit of sinking air, and their reaction when they find themselves sinking is to slow down even more, which is the wrong thing to do. You actually need to speed up a little bit. Even though you'll go down faster, you'll go through the sinking air more quickly. And very often you'll watch a group of pilots flying around, the experienced pilots gradually get higher and higher. It's not because they're using the lift better, well, it might be part of it, it's because they're managing the sinking air better. Everybody's going up the same in the lift, and then the experienced pilot thinks, oh right, I'm losing my lift here, I'll speed up and get to the next bit quickly, whereas the inexperienced pilot hangs around slowly. So what you can take from this is that very often if you're not actually in lift, you should be flying a little bit faster. But there's other things you can get out of here as well. You can actually use the axis. I don't propose to go into it now, but you can work out the best speed to fly with a certain amount of headwind or lifting or sinking air, and that will tell you the best speed to fly. Okay, so that's a polar curve anyway, it's just a map of the performance of your glider. So off here you can get, for example, you can ask yourself a question like, what's the best speed to fly with a 15 mile an hour headwind? And you can draw the line from the appropriate point on the axis, which will give you an intersecting point on the curve and let you know what the best speed is. Okay, faster than you think is the answer. Okay, next thing I want to get onto here is turning and wing loading. I mentioned earlier on that weight operates straight downwards, but that's not strictly true. When you're banked, then everything gets thrown off at a slight angle. So when you've got a bank on and you're turning, you've still got a vertical component of lift, but you've also got a slight horizontal component of lift, which are marked in here. So there's a vertical lift, there is the horizontal lift. And because we increase our wing loading, we effectively increase our weight slightly when we're banked and turning. So the resultant of the horizontal and the vertical lift is off now at a slight angle, obviously straight up your king post if you've got one. Why is this important? Well, it doesn't matter too much at low angles of bank. At a 30-degree angle of bank, you're only increasing your load by about 10% or something like that. So it's not a huge issue. But if you have a steep angle of bank, 60-degree angle of bank, and you're maintaining your altitude, you'll be loading up to 2G. You know, you actually put quite a lot of force extra on the glider, and if you increase your wing loading, you increase your angle of attack. You lower the angle of attack at which the stall occurs. So at 2G, it's about 140% the speed at which you reach the stall is. So sounds a bit complicated. All you need to know is that you can turn or you can fly slowly, but you can't turn and fly slowly simultaneously. And I mention this because this is a common cause of problems. Out there in normal flight, people are quite happy. They let the glider go a bit faster in the turn, and when they come into land, they're trying to slow down and turn, and that's where people drop their wing or they drop their nose and they have all sorts of problems. You can't do it, and this is why all aircraft have a flight plan where they come around, they do a base leg and they do finals, and they slow right down on their finals as they come in. Aviation history is littered with accidents of people who tried to slow down on their final turn. So this is something we need to know as hang glider pilots. you know, get yourself set up, get into wind on your finals, then slow right down. Don't slow down as you turn. And this is the reason, because the glider will stall more quickly than you are expecting. Okay, right, so that's a quick introduction to some of the technical terms and the sort of principles of flight that are specific to hang gliders. So I hope you found that useful.